Gayet net geliyor.
Okeydir. Yayın okey mi? Yes. Okey. Ekran paylaşmadım. Yayın okey mi? Herkes tamam görür mü şu an?
Aynen. Güzel.
Okeydir. Okey, başlayabiliriz o zaman. Atölye İngilizce olacak. Yalnız Türkçe soru sormak isterseniz sorabilirsiniz. Problem yok. Ben İngilizceye çevirip kayda söylerim onu. Okay. Welcome to the workshop on object-oriented programming. My name is Tecelli. I'm a game developer. I've been doing this for a few years, and I just wanted to tell you guys a little bit about why we use object-oriented programming. So let's start. What even is an object? Now, everybody always talks about object-oriented programming, but first we need to understand what they mean by objects when they say object-oriented programming. So if we want to boil things down, we can say that an object is just a container that holds some code and data. Now, there's also the question of what kind of data and what kind of code is this object going to contain. And we can say that the thing that defines our object is the class that this object was created from. Now, let's talk about what a class and an object is a little bit further. So we can think of the classic analogy that a class is more like the blueprints of a car, and the object is actually the car itself. So the class doesn't do the job for the most part, except for some exceptions. The object is what's doing the real job, but we wouldn't be able to create an object without the class that defines it. So now that we know what an object is, let's get into why we use object-oriented programming. Well, the simple answer is because objects make sense to us. Because we're human, we live in a world that is full of objects. You have your phone, your computer, these are all objects. So it makes sense that we would model our programs using things that make sense to us. And it's really easy to think about objects this way, to think about how they interact with other objects and how they would be in the real world. So, talking about games programming, we can say that games are also often mimicking things that are in real life. Games also have objects in them. They also have things that you interact with. So, it makes sense when making games to also use object-oriented programming. So let's see a little bit of an example of code. This is C++ code. I don't want you guys to get scared by C++. I'm just showing these examples as a general idea. You don't need to understand the syntax or remember what's going on. Just as what's here, you see we have our class. That's a car. It's the definition of what a car should be in our program. So it can have a position, it can have a speed, it has 4 wheels, it has 5 seats, it has the ability to start and stop. Now, you can see that there's 2 sections in the class called public and private. These are important in object-oriented programming so that we can make our classes or objects more easy to expand upon, more easy to use. Because if every person who needed to drive a car needed to know how an engine worked and how to do stuff inside the engine, we wouldn't be able to have people driving cars. That's why we need this simplification where there's some things going on under the hood in our private section, while the things that we really need to interact with goes on in the public section. In C++, the way this works is that private things are only accessible to the class itself, and public things are accessible from outside of the class. Or in the case of objects, they're accessible to from outside of the object. Here, for example, you see that we have a start function and a stop function. And these functions are exposed to the outside. You can use them from the outside. And the actual action of starting or stopping that goes on inside the engine is not exposed to our programmers or our users. Only from inside of the car class can we actually touch and interact with the engine. And just to show how an object is different from a class, in the right, in our main function, we created the Batmobile as we defined it as a car class. So it is an object of type car. And when we're accessing it, we access it from the Batmobile to start it and stop it, not from the car itself, because the blueprints don't have the ability to start or stop. It's only the objects that come from the blueprints. Now, I'd like to show some examples from C++ code. This is going to be the major part of the workshop. Now, I've written these in Raylib for rendering. You can find Raylib at raylib.com if you're interested. You don't need to follow along in this workshop because I'm going to be using Raylib and you'd need to install that beforehand, and I didn't want to complicate things. So let me get that ready. And in the meantime, if anybody has any questions so far or anything they want me to expand upon, I can take that now. I'm gonna stop the screen share real quick so I can switch it to the other screen. Yes. So first of all, is the code visible? After I share the screen, of course. Yes. Is the screen clear? I'll increase the font a little bit. Yes. So I've put all the boilerplate codes down here in the main function, but all you need to know about this code is we have a start function that's called at the start of our game, and we have an update function that's called at the end of each frame, and a draw that actually draws the current frame. So let's say we wanted to create a... One second, please. We wanted to create some game where we have some bullets that can show up on the screen. So here you can see I created a bullet X position and a bullet Y position. And we have this function that can draw a circle, and it takes the X position, Y position, the radius, and a color for our bullets. This function and the red is defined in the Raylib library, so we don't need to worry about how those work under the hood. You can see we're defining globally our X position and Y position. I just set them to screen width over 2 and screen height over 2 just so that they'll be at the center of the screen. So if I run this, It should compile and run. Yeah, I hope that's visible. We have a little red circle at the center of our screen. Now, let's say we wanted to create a few more red circles. So to do that, we'd either have to go in without using anything else. We could call this bullet 1. And then we would have to create a different bullet XY position and then call this function again with both of them. But even in simple terms without classes, we can say that the better way of creating more than one bullet would be to use arrays. So if we use an array, let's call this bullets X, and let's say we have 5 bullets. We can make these arrays, and we can define some values for them. So the first bullet can be at the pixel 100, the second one can be at 200. Let's make that 3 bullets for now, just to speed things up. And 300, and we can set all of the other ones to their Y positions to 200, all of them. So they'll be around the center of the screen. So now we have our values, our X values and our Y values. They're still just number values, they're integer values. And now we're going to call this function back to back with a little for loop. We have 3 bullets. So now we're just going to read from our array that we just created. Yeah. So now if we run our code, it's going to take a second to compile. We have our 3 dots, and they're right next to each other. Now, you can see that this is cumbersome, that we're trying to, whenever we want to add something else, we have to come here, we have to change the size of the array, we have to add the next element, and one array holds all the X positions, and the other array holds all the Y positions. And you can imagine that you could, if you increase the size of this, you could accidentally erase one extra from the X coordinates, and then all of your Y coordinates and X coordinates would be shifted. You'd have everything in the wrong position. So, just to show a cleaner example, we can look at here. We did the exact same thing. Yeah, and before we move on to better solutions, let's see how we would actually change these values if we wanted to. Just like accessing any array, we can choose by index some array, some bullets, and we can set their X value to something else. And this would change it in the array, and it would change down here when we're actually printing them. So you can imagine that since we're drawing this with the Raylib library, they would have some solution to think about coordinates, because it's kind of difficult to every time think of the X coordinate and Y coordinate as separate things, when really we're only talking about a position, and a position would have both the X coordinate and Y coordinate inside it. So that's where the vector2 struct comes in. It's something like a class. This vector2, we can create a new one and say bullet position. We'll name it bullet position, and if I just write it down here just to show it, it has an X coordinate and a Y coordinate. Pretty much exactly what we need, and the people making Raylib actually thought about this. There's a different version of the draw circle function called draw circle v, that instead of, as you see here, instead of taking an X coordinate and Y coordinate for the circle to be drawn, actually takes a vector2. So instead of passing the 2 arguments, we can pass 1 argument that would take care of both of them. So let's quickly look at how that would be if we switch these to vector 2. So I have that ready here. Here, instead of having 2 separate arrays, we can have 1 array that creates these vector 2s inside of it. So immediately you can see that it's much more comfortable to read, because instead of having to see that the x coordinate of the thing is here and the y coordinate is down here, in the vector version we can have the x coordinate and y coordinate next to each other for each circle. So for each of our bullets we define an x and y position directly next to each other, and if we wanted to add more, we just add them here and we would have an extra bullet that was created. And down here, the position, this is how we would call this with the normal draw circle function. And if we quickly switch this to the draw circle v version, you can see that we can just pass the position in, and we can call them with less parameters. I have different starting positions here, so let's just run this just to see what it looks like. Yeah, we have our 3 circles here, and we have the other one that in the start function I'm setting to the center of the screen. Now let's say we wanted to add more options to our bullets. Let's say we want our bullets to have different colors or different sizes. How would we do that? Now here we would just have to add a separate array for size and a separate array for color. So if we look at those, we've created some bullet sizes and some bullet colors. So first one's red, then green, then blue, then magenta. And I've changed the draw circle function to take the position, the size, and the color. As you see, we're just passing the specific index of each array separately to each parameter of the draw circle function. And if we just run that real quick, you can see that there. This is also the example that adds movement to them. You can see if we want them to move constantly, we have this update function that runs each frame, and we can add to the x coordinate and the y coordinate of the bullets positions to move them. And in this code we're just looping over all of them and moving them diagonally. We're moving their x coordinate and y coordinate together. But again, this is something that you would want to be able to do in one line instead of having to add the x coordinate and the y coordinate separately. So let's just show an example of how these objects could help us to simplify our code a little bit. Let's say we have a function that's called vector add. This is going to sum up 2 vectors for us. As you see here, we're adding 1 to the x and 1 to the y, so we're essentially adding the 1, 1 vector to our xy vector. So the way we write this in C++ is we write the return value first, the type of the return value. Here it's going to be vector 2. And we write the name of the function that we want, and then some parentheses and brackets. And the parentheses are going to have our parameters that we want. So it's going to have a vector 2 for the left value, and a vector 2 for the right value. And we can just do what we did down there, where we're doing the x position plus the x position and y position plus the y position. We can create a new vector. We can create this with the curly braces. I used it up here before. We can do L, dot x and L dot y. And this dot is what allows us to access the things inside of the object. Let me fix that real quick. It was supposed to be L dot x plus R dot x because we're adding the x coordinates together and we're adding the y coordinates together. So now, this part where in 2 lines we're summing up the x coordinates and the y coordinates can be simplified to be the specific bullet's position equals vector add. We can add its position plus a new, well, not plus, but comma, a new vector, and we call it 1, 1. So now if we run this code, you'll see that it will run exactly the same way. Yes, I made a mistake right here. It's the x coordinates plus the y coordinates of the 2 different vectors. And they move exactly the same way as they would have before. So this is just the most basic way that we can simplify these. And now we'll just review what we've done so far. We have our vector2 objects that we can hold the x coordinate and the y coordinate together here. We have them all in arrays for each different bullet that we want to have, and we have different sizes defined and different colors defined. And we are using our add function to add these values together so that we don't have to add them separately, and we have our draw function that's drawing these bullets. Now let's start to look at the way to do this in classes. So if you remember from how I showed it earlier, to define a class in C++, we have to say class. We give it the class name. So in this case, it's going to be a bullet. And we use our curly braces to show it. And we have a public and a private part inside here. And in C++, if you don't write these, it assumes that everything you write is private. So since we're going to access our position, size, and color from outside, we can write them in the public section. So our bullet is going to have a vector2, that's a position. It's going to have an integer, that's for the size. And it's going to have a color for the color. So this is the simplest way to create a class. And to use this class, just as an example, also there is a semicolon at the end of the class definition. To simply use this class, I'm going to, just to show an example, come to my draw function. I'm going to define a new bullet here. So this should create the bullet, and then we can set the bullet's position to whatever we want, its color to whatever we want, and we can create it. And then down here, after we've added all of those, we would come to this part, and when we were drawing it, we would use bullet.position and bullet.color. Wanted size first, so bullet size. So this would draw our bullet. you can see the comparison of how the two different implementations work, where here we had an array that we were picking values from. We had different arrays for each property that we wanted our bullet to have. Now we have this bullet object that contains all of it all together inside. So if we switch all of this to the class way of doing things, I'll talk about this first. This is the constructor of the class. This is how C++ handles creating the objects with values inside them. So here in the previous one, since we don't have a constructor here, when I create this bullet, it in fact creates a bullet with all the default values it has for these. Or in some cases with C or C++, you would get some random garbage data because you're not initializing your variables. If we want to force the programmer to set these values, then we can create a constructor that requires these values as parameters. So we have this bullet constructor that takes a position, a size, and a color, and it sets those values as it's being created. So the constructor is just essentially a function that gets called when the object is being created. So we've used it here. We have our bullets array now. And when we're constructing this bullets array, we create a vector2 and pass it into the constructor, the size, and pass it to the constructor, and the color, and pass them to the constructor. So in one line, we can give all of the information to the of the bullet and create this bullet. And to use it, as we showed before, we have our array that holds all of the bullets. And you can see from the difference from the previous example is that here we had 3 different arrays that we were reading values from, and here we have one singular array that holds all of the values for all of the bullets. And it's better organized for the programmer. It's more easy to understand because you have this one object that has all of the values of color, size, and position inside it. Now, this only uses the data side of bullets. As we said, the classes help us organize the data of the objects that we want, of the real-world objects that we're trying to model. So let's talk about how we can also put code inside of this bullet class. So you can see that we have the bullet constructor. Technically, the bullet constructor is also a function, so it is code being executed. So down here, we have this vector2 add function that's being called over and over for each position, each bullet. But our programmer shouldn't really care how this is being handled, for example. So if we wanted to simplify this, we can come here and create a new function called move. And our move function can take a vector2. I'm going to call it amount here for the amount it moved. And in here we can call this function the vector2 add function. So we can say position equals vector2 add, our position, and our amount. So now, if we wanted to use this, instead of saying the bullet's position equals its previous position plus 1, 1, we can just say bullet I move by 1, 1. So this simplifies the usage a lot better, as we don't need to know how the object actually moves in the background the programmer doesn't need to know the specifics. We just have this move function, and we know that we pass some vector inside it, and it moves by that amount. So that's a nice simplification we can do the classes. And yeah, similarly to the move function, we can also create a draw function. For those wondering, the void here means that the function is not returning any values, where here we were returning the vector too. So here, if we just copy this line and come to our own draw function, we can just pass, since we're inside the object, we can pass our position, our size, and our color. So now we don't even need to know what function to draw this with. We just call the bullets draw function when we want to draw, and we can draw. So now you can see that we don't need to know, a programmer using this class doesn't need to know how this actually draws in the background. It just draws itself when you call the draw function. For those who haven't used classes in programming languages before, or used C or something, they might say that this draw has the same name as this draw, so wouldn't there be a compilation error or some conflict? But since this draw is inside of our bullet class and can only be accessed through our bullet class, it actually does not create any conflict, since they have different scopes. If we just wrote draw, this would call the function out here, but going to a bullet object and saying point draw is what draws the actual bullet. It calls the draw function inside of the bullet. So yeah, we can get back to our slides, and I'd like to take a small break here. It's been 30 minutes. We can take a 10-minute break, and we'll get into inheritance. Inheritance is a big subject, so I don't want to tire anyone. But before we go on break, does anybody have any questions? Okay, then we can go on break. Birazdan başlayacak. Evet, başlayabilirim. Welcome back from the break. Now we are going to get into the big subject of inheritance. So, in general terms, what inheritance is a class can have a parent class that it inherits from. And it will have all of the members and all of the attributes and all of the values or functions that the parent has, it will also have. So it creates this common functionality, so we wouldn't have to rewrite a bunch of stuff. We wouldn't have to rewrite a bunch of stuff to create some things with common functionalities, and it simplifies our code when we have to have things that do similar things. So as a basic example, we can have a cat class and a dog class that both inherit from the animal class. So we can have this animal class that has a virtual function. Virtual means that the classes that inherit this class are going to change this function. They're going to give their own implementations of the function. So we have the speak function that returns a string. So in our dog class that is inheriting animal, we have the speak function again that returns a string. And next to it, we see that there's the override keyword. And in C++, the override keyword means that it is overriding a virtual function that is defined in its parent class. In C++, it's not mandatory to write the override keyword, but it makes sure that it is overriding something, so that if you go back and you change the name of the speak function in the animal class, the compiler will give you an error saying that this speak function doesn't have a virtual function that it is overriding. So let's look at what these classes are actually doing. So we have this animal class with the speak function and the dog and cat classes that are overriding the speak function. So the dog class, as you see, returns woof, and the cat class returns meow. So you might say that, oh, the dog function and the cat function both have the speak, or rather, the dog class and the cat class both have a speak function. Why did we need this animal class? Why can't we just call speak on both of them separately without any inheritance? While that's technically possible, what inheritance allows us to do is put these dogs and cats into similar containers, into the same array. So normally in C++, the way the strong typing works is that the compiler has to know what kind of class is inside an array, or what kind of class an object is, or what kind of class a parameter to a function is. So in our case, we can create an array of animals, and we can put both dogs and cats in there, and call the speak function on both of them. Now, if we did that, we still wouldn't be able to add different functionality to dog class and call that separately. Like if we had a different function inside of the dog class that's, let's say, lick, that a cat couldn't do. Not a perfect example, but let's assume that in this world that our game is in, the dog can lick, but the cat can't. If we had an array of animals, we wouldn't be able to call the lick function on the elements of the array, of the animal array, because the animal class doesn't have a definition of a lick function. So only the common functionality, the common definitions are usable from the common class. Now, although in our example, we showed cats and dogs both inheriting from one class, we can also have classes inherit from classes that inherit from other classes. In this example, we have the animal class, and it has two different classes that inherit from it that are bird and mammal, and we have cat and dog inheriting from mammal, and chicken and parrot inheriting from bird. So in this case, we can say that a chicken is a bird, and a chicken is an animal. So the chicken contains all the functionality that the animal does and that the bird does. Now, before continuing further, I'll show a code example how we can use this. You can see here I'm creating a print speech function that can print the result of the speak function of any animal. So here we created a cat and we created a dog. And you can see I'm passing the cat and the dog separately into the print speech functions. And this would work. When we call this, it would first print meow and then print dog. Sorry, not dog. It would print wolf from inside the dog class. There is a difference here in C++. If we were using C#, we would be able to just pass the animal, the cat and dog, directly to the print speech function. But the way inheritance works in C++ is that we need to pass the animals in as pointers. I'll go into detail on pointers later if we have extra time, but it's a very C++ specific thing where it's just giving us the address in memory of where the animal is before it accesses it, and the arrow is the same as a period, just for pointers. So essentially we just have this function that takes either cat or dog, doesn't matter, and it can print the result of the speak function. One minor detail in C++. In C++, a class can inherit from multiple classes at the same time. So if we had a mammal that was also a bird, we would be able to create that in C++. However, that creates a lot of complications and is not suggested to be done. However, in C#, for example, a class can only inherit from a single class. But C# has different solutions for being able to give structure of multiple classes. So, if OOP is so great, why shouldn't we use it everywhere? For that, I have to explain a little bit about how memory works in the computer. So, as we showed in our previous examples, we have this class that has a position, a size, and a color. So, with the position, size, and color, you can imagine that these are sitting back to back in memory. So in memory where the bullets section starts, we have space for a vector 2, which is 2 integers back to back, and we have a space for a float, and we have a space for a color. So you can imagine if we have an array of bullets like this, the space goes integer, integer, float, color. So it's 2 integers, float for the size and the color. So these are quite heterogeneous, where the sections are the same thing, but there's different kinds of memory, different kinds of values placed back to back. But if we look at our old array example, with the colors and the sizes, here we have all of the positions back to back in memory, and all of the sizes back to back in memory, and all of the colors back to back in memory. So for the most part, programmers don't need to think about how their memory is aligned and how it's placed. But if you're running something that's performance sensitive, and a lot of time games are, then you start having to think about these things. So an alternative to object-oriented programming is data-oriented design, which they're not exactly opposites of each other. They can be used together in some ways. Like, one doesn't mean the other one can't exist. So in data-oriented design, we try to organize our data in this way, where things that make sense together are placed nearby in memory. And the general idea of objects don't really exist in the memory side of things. Now, the reason why this matters is because the CPU is very fast and memory is very slow. So when we try to access the data from one bullet, the CPU brings other parts of nearby memory into a faster memory called the cache memory in the computer. So it basically remembers what's nearby of this memory piece. So this has an advantage, as in, if a lot of my code doesn't care about the size or the color of an object, of a bullet, but it cares about the positions, then I can organize all my positions to be next to each other so that the CPU doesn't have to spend time waiting for more memory to be fetched. Since all of the memory is packed nearby, it can just, since it remembers the things nearby, it can take the things and it can use the values that it already remembers. So if I try to show the general idea, if my ASCII art skills will help me here. In object-oriented programming, we have something like this, where it's integer, float color. And the memory is organized like this. Each letter being one memory location, approximately. So when we try to read this object, we can imagine that it brings something that's next to it as well. So it can read all of this information very quickly. But if we're only interested in the positions, then it reads this data, and then it has to jump to this data, and then it has to jump to this data. And if our classes aren't even arranged in memory, which is quite possible if we're creating these objects dynamically and we're not paying attention to where the memory is placed, we can have them be fragmented, where they're all in completely different parts of memory. So when we read this, the next element is actually really far away in the memory, and the the CPU would have to jump to that memory to read it. And since it's not nearby the other thing, there's no way it can remember that value with the cache memory, because it can only bring into cache the values that are nearby. And this is obviously a gross oversimplification of how cache memory works, but we don't need to go into detail that much for the purposes of our class. Yeah. And if we organize them in the data-oriented way, even organizing them this way is better than having them fragmented, just having them back-to-back. But if we have specialized ways of interacting with the data differently, like some functions that are only going to run on the positions constantly, then it would be a better idea to have the positions oriented next to each other in the memory. Let me just go through my notes to see if we had anything that we didn't mention. And to explain inheritance better, I'm going to show some Unity code. While we're waiting for the project to open, I'll just quickly mention about inheritance one more thing in C++. You can see here we wrote public next to the class name. This is also very special to C++, where you have to define whether you inherit this publicly or privately. So if I privately inherit from animal, other classes won't be able to access the members that it got from the animal class, so other objects, other classes, other functions wouldn't be able to access the speak function of the dog because it's part of the animal class. And yes, this is our Unity example. I'm sorry if it's quite small. I'll explain what's going on. So in this little dummy example, we have this floating ball, which let's assume is a coin. We can click on it to pick it up. And when we pick it up, it gets destroyed. And here is a door. If I can show the animation. Yeah, it has this animation where it can open. And it has an animation to close as well. So if I go in just to show how this works inside the game, I click the door and it opens. And I click it again and it closes. And if I click this ball, I pick it up. Now let's look at the code that goes on behind this. So this is the naive solution without using any kind of inheritance. This solution, as it opens, I'll explain, uses the Unity tag system. I've seen a lot of beginners use this system, and it's very easy to prototype with it, but I'm going to be showing you why it's not very scalable, why it becomes a problem going further. So you can see on our coin here, we have the tag of coin, and on our door, we have the tag of door. It might not be very visible on the presentation, but I'll be reading every part that's important. So if we inspect the code here, Writer is still trying to open. So we have this naive interaction class that is a monobehavior. That's what all Unity scripts inherit from. This is what gives you the important values that let this be an object, let this attach to an object in Unity. I'm sure a lot of you are used to just being able to write game object when they're in a Unity function. But the only reason this works is because this is a value defined somewhere inside the monobehavior class. So actually, we can inspect what's inside the monobehavior with the decompiler. And you see that monobehavior inherits from behavior, and behavior inherits from component, and component inherits from object, and object is the Unity object, not necessarily a game object. So you can see how things can inherit from other things who inherit from other things. So to understand what this code does, let's go line by line. We're in our update function. So when a left click occurs, we are essentially doing a raycast. So we are doing a raycast from our position forward. So the way this is looking, this script is attached to our camera, by the way. So it's the way our camera is looking. So what a raycast does is it uses the Unity physics system to basically draw a line from the starting position in this direction, and it basically detects things in this line. And it has a max reach value that we also are showing. So we have this hit value, this hit object, that is of type raycast hit. And inside it, it has some information about how our raycast hit the first object that it got. And from the hit, we can actually get the game object of the object that we've hit. So in this interaction code, we have some checks that are checking if the hit object has the tag of door, or if the hit object has the tag of coin. So our specific code is inside of the naive interaction class, so in the interaction class that is on our player. So in here, we're just getting the animator and starting the animation. Now I want you to realize that in this case, this class that is inside our player has to know how to call the animation of the door. So it needs to know specifically what animation to start, and that it runs with an animator. And also has to do a get component call, which isn't a very efficient call in Unity. And in our coin interaction, we are just destroying the object. If we actually had a coin system that was counting how many coins we have, we would also have that code in here. So this works. As far as working, this is absolutely fine. But if you think, I'm going to change this door's animation from open to open slowly, for example, if I want to add that different functionality, or if I want to trigger something else when the door opens, you can see how I would have to add a lot of things in here. I would have a lot of code in this interaction class that has to handle just what a door does, what a door is supposed to do. Same with the coin, same with other objects. And you can also see that once we have a lot of objects, a lot of different interactions, this is going to be a huge if-else-if ladder that is going to be going on for a long time. And having to compare with every single version of the possible interactions. So let's look at a different solution to this. Let's do it. Let's see how we can fix this with classes that use inheritance. Well, before inheritance, let's think about how we can solve the first problem. The first problem is that our interaction class is what's controlling how a door works. So it should be intuitive that the door should have a class of its own that handles how a door works. Our player shouldn't have to know how a door works, our player class. The door should know how to work on its own. And the person programming this should be able to just tell the door to open, not have to know how the door is supposed to be opened. So the simplest example is to have a door class and a coin class. And we still would need to do a get component here. But instead of getting the animator and calling the play function on it, if we have a door class, we can just do get component door. If we had a door class. And this door class would have an open function inside it, and we would be able to call the open function here. But there is a better way with inheritance. So if I open this class, you can see this has exactly what I was talking about. Instead of calling get component every time it needs to be interacted with, it calls get component once when it starts, and it has an interact function which has the actual code inside it to execute the opening. So if we're going to use this, we only need to call the interact function on here. But this isn't just a door class. It inherits from interactable object. Because this is a class that I have created beforehand. So an interactable object class is an abstract class. Abstract class means this interactable object cannot be created on its own. So although interactable object is a class, an object that is of type interactable object cannot exist. So because this is just a template class. This is just something that we're going to inherit from later on. It's not something that is going to be created on its own. And it has an abstract function in it. And abstract function also means that the classes that are inheriting from this class, so the child classes, are forced to create their own interact function. If it was virtual, it would be optional to create interact function. And if they didn't create an interact function on a virtual function, it would just call default interaction that's written in the parent class. So how can we rewrite our interaction code to work with these classes? Well, I have that version right here. As you see, it's the same logic. When we press the left mouse button, we shoot a raycast the exact same way as we did earlier. But now, instead of having a bunch of ifs and else ifs to compare tags, we get the game object and we do a get component call for interactable object. Now, I've done this with the try-get component function, so I want to just show how this would work without that. And this will be an example of what the try-get component function does as well. So let me comment this out really quickly, and I'll rewrite it without using try-get component just to have the example. Also, a little Unity tip. All components can use the get component function. So here, normally you would go game object to get the game object and then do get component, because Collider is a component, not the game object itself. But in Unity, you can actually call get component on other components as well. You don't need to call it on the game object. This will technically call it on the game object in the background. So this is how we would do a get component call without the try get component version. And then we would have to check if our interactable is not equal to null. So it checks if the object we hit has the interactable object class, and then we check if it actually had that class, because this just tries to get it, and it will return null if it doesn't have the object. And null just means it is nothing. It has no type value. And inside here, we would do the interaction. Now, the way the try-get component function works is that you create... I'll just comment this out. You create the interactable variable, the one we defined up here. You can create it inside the parameters of the function. So it tries to get it, and if it did get it, it will return true and execute the inside of the if. And if it can't find this component, it will return false, and this if statement will not execute. So here we have the interactable, and as you can see, simply we are just calling the interact function on it. So now this player class, this interaction class, does not know what type of object it hit even. It just knows that it hit an interactable object and it will interact with it. Any of the specific implementation for any object is going to be done inside that object through this class. But also, just a side note, I'm not sure if I mentioned this. In Unity, if you want this class to be able to be added as a component to scripts, you will have to inherit from monobehavior on your abstract class. But in C#, there's an even better solution to this problem. Because here, our door has to inherit from interactable object. There's no way it can inherit from a different class now. So there's a way that we can do this even better, which is called interfaces in C#. So an interface looks like this. It looks a lot like what we had earlier with the interactable object, except instead of abstract class, we have said interface, and we just defined the name of the function. We didn't use abstract or public. So the way interfaces work is basically one class can inherit from multiple interfaces at the same time. But the interfaces have a huge limitation where in classes, in virtual or abstract classes, I can actually write code inside of this class that is possible to run from the class that's inheriting it or from the outside. So I could have a destroy object class in here, a destroy object function that would be common to all classes that inherit interactable object. But in interfaces don't support data or default function definitions. Actually, in the new version of C#, it does support the default value for functions, the default definitions. So how would our code change here if we use our interfaces? It's pretty much the exact same. We're just using our interface's name here, which, as a convention, interfaces have the prefix capital I in C#. It's not, you don't have to do this, but it's the general convention. So in our case, the interface is called IInteractable. So our class is saying that I am an interactable. So it worked the exact same way as the inheritance one, except instead of the interactable object, we're using our IInteractable function. And the difference in our coin and door objects is that we just add a comma and we write IInteractable next to it. So you can see here that the door is inheriting from monobehavior and also implementing the IInteractable class interface. Sorry. So this, the fact that we can add multiple interfaces and different values makes it really easy to expand upon things and really easy to organize our classes into subgroups. And just to show a different example, if we wanted all of these three interaction classes to exist together, we could create a central parent class that defined some of these things, like the physics raycast, so that we wouldn't need to run this. So I'm going to create a simple thing like that here. If we create a new, Unity script monobehavior, let's create an interaction class. And here, let's use all the things we've used so far, all the things we've talked about so far. So the update function. Let's say we want the interaction, the specific interaction classes to only define the inside of this raycast. So we could copy most of this code. Now, since we're using this as a class and not an interface, we will have to inherit from monobehavior in our interaction code. So this inherits from monobehavior. And the general parts, like the getting the mouse button and actually doing the raycast, we can keep, and the rest of the specific code we can remove. And this update function, I'm just going to make it virtual. And I'm going to make it protected. So virtual means classes that inherit this can overwrite this function. And protected is just like private in that other classes won't be able to access it, but classes that are inheriting it will be able to use it. So we can define another function that is protected. And I'm going to make it abstract. And it's going to be called the interact with function. And this is just going to get a game object. Interacted. Since it's abstract, we don't define the inside of it, we just define the thing. And I forgot to write a return type here. It is going to return nothing, so it's going to be void. And since we have an abstract function, this forces us to make the class also abstract. Because if you have an abstract function and you initialized or you instantiated an interaction object, this function would exist, but it would have no definition, which is obvious that it could create a problem. So all we want to do here is call the interact with function. And we want to pass the game object of the thing we interacted with. So you might see where we're going with this, but in case you don't, we have this function that's just defined by name. What it does is not defined as an abstract function. So this is going to be filled in when we inherit from this class. Abstract and Neldum. Okay, so to reiterate what abstract means. Abstract is a class that needs to be inherited from. We cannot use this class without inheriting from it. So if I went to a different class, like this coin class, and tried to say interaction class, like interaction X, and say equals a new interaction. It immediately gives an error, and it says interaction is an abstract class, and so you cannot create an interaction object. So it can only be inherited from, it cannot be instantiated to an object on its own. So, and it's similar with abstract functions, where abstract functions need to be overridden. You can't inherit from the interaction class without overriding the abstract functions. And we'll see that in a second too. So basically what this code is going to do is the same thing as before, but it gets the object that it hit, and passes it to the interact with function, even though the interact with function doesn't have anything defined yet. Now, if I go to this naive interaction class and replace the mono behavior with interaction so that it inherits from it, you see I immediately get an error, and it says the abstract inherited member is not implemented. So in Rider or in Visual Studio, if you do Alt-Enter for the quick actions, it gives you an option to implement the missing members. So it just created that for us here, making it protected, override the interact with function, and has the game object of interacted. So in this part, we shouldn't have an update function here. I should also mention that if you have a virtual function in your base class and you create the same function with the same name but do not override it, then it destroys this function. So it makes this function inaccessible because we're redefining the update function. And it warns us here that if we want to actually redefine it, if that is what we want, then we should write the new keyword here, which is just something special to C++. But we actually don't need a update function here. So what I'm going to do is I'm going to take the actual functionality part of this and replace the hit objects with our interacted class. Our interacted object, rather. And now we have no use for the update function anymore. Now, because we inherit from interaction, the update function is going to continue to be called from Unity. It is going to continue to run every frame. And it will call the interact with function. And the interact with function is going to call this, and it's going to run the code that we previously had. Is there any questions so far? Because inheritance can be very confusing sometimes. Any questions on the Discord? I guess not. Okay, I just want to show one more trick here. Let's say in our naive interaction class, we now want to use the update function separately. So if we do protected override and do update, well, it already showed what I was going to show, but if we do this, now the update function down here in the interaction class is not going to be called anymore because we are overriding it. We're replacing it with this new code that we're writing here. Now, if you want to write new code, but still have the thing be executed in the base class, then what we can do is we can say base.update. And what this does is it goes to the base class and calls the update function there. So basically, Unity is calling this update function, the overridden one, and that is going down to the base class and calling the update function. So here, if we wanted to do different things like debug log every frame, then we would be able to do this and the rest of the code would still work. The reason Rider, the IDE, is making this gray is because it doesn't do anything. If we hadn't written this at all, it would be calling this base update anyway. So it's making this gray to show that it is not being used. Yeah, I think that's about all for this so far. Is there anything else anybody wanted to know about object-oriented programming or any other thing? Mm-hmm. Evet. Okay. Okay, if there's birden fazla base class buradan we cannot inherit from multiple classes, but we can inherit from multiple interfaces. So we can't have multiple code, like data including things, but we can inherit from multiple interfaces, which for 90% of the time handles everything we need. In C++, it is possible to inherit from multiple classes, but that creates a nightmare, because if you can have two functions that are both named the same way in the two different classes, and it's very ambiguous which one it's actually accessing when you try to call that function. And especially with data, if you can inherit from, let's say you inherited from animal and dog at the same time. So dog also inherits from animal. So now you're inheriting from animal twice. So you have all of the data for animal twice. So it can create very complicated things when you're inheriting from multiple classes. So interface is a good solution for this. Yeah, I guess that's all for today. If there's nothing else, I'll be closing the stream. Okay, I guess that's it. Thanks everyone for listening. I just want to say that if you have any other questions or anything else that you thought of afterwards about C++, object-oriented programming, C#, Unity, anything else, feel free to message me on Discord or wherever you can find me. I'd be happy to help. So thank you all for listening.